So good afternoon, everybody. If you could find a seat and please silence your phones like I'm doing right now. Welcome to our stakeholder group meeting for our regional groundwater monitoring effort with the U.S. Geological Survey. We've got 4 presentations today that should cover a full 2-hour period or 3-hour period, and each one is scheduled to last about 20 minutes or so, and will allow 10 minutes worth of Q&A after that. We've got a brief intermission plan, but if folks want to continue, we have critical mass, we'll go ahead and continue on. I wanted to say thanks and for everybody to come today. This is our second semi-annual meeting that we've had regarding the findings that the USGS has been working on for us in the regional monitoring program. It's something that's important to us. Obviously, we're directed to do this under our statutory obligation with SB4, as well as our model criteria that was adopted by our board a couple of years ago to continue a regional groundwater monitoring effort associated with oil and gas activities in California. A few housekeeping issues with respect to the meeting here. If there's an alarm that goes off, there's no scheduled drill today, so if you hear an alarm go off, there'll be an announcement giving us direction on what to do, but typically on this floor we'll evacuate down the stairs and over to Cesar Chavez Park, so hopefully that won't happen today since it's so warm. So the 4 talks today will focus on studies on the west side of Kern County predominantly in the areas of the Lost Hills and Bell Ridge oil fields. The first talk will be by Jan Gillespie, and that's talking about the aquifer architecture and salinity in the Tulare Formation. The second talk will be Lindsay Ball, our geophysicist with USGS, talking about groundwater salinity using airborne geophysics. The third talk will be by Pete McMahon, Regional Geochemistry of Oilfield Water. And finally, Tracy Davis will go over groundwater quality results on the west side of Kern County. So now that I've covered everything, here's Jonathan, would you like to say a few things? I didn't say everything.
Mostly, I want to apologize for being late. I got a call from my daughter right before coming down here, and that took precedent. I'm sorry. But thank you all for being here. This is really important to us, and I hope it's important to you, and I'm looking forward to seeing the results. So, that's enough.
All right, so we'll kick things off with our first speaker, unless Kim wants to say something. She's approaching the dais. Okay, go ahead. Come on, Kim.
A lot of people on the phone too, so I'm kind of. That'd be great. We have folks here are going to be staying after the scheduled completion of this meeting. So if anybody wants to get into a really detailed technical discussion, level of detail that we did not cover today, please feel free to grab one of them, and we'll see at the end whether people want to continue these conversations. How many people actually want to stay in the room for those? So I want to give you a quick overview of the USGS work on the regional monitoring program. And John already gave you this overview and status, so I'm going to give an overview, we're going to give the talks, and then we're going to give a wrap-up, and then we'll see where people want to go. I want to remind everybody that these are the questions that the regional monitoring program is designed to answer. And they're basically, where in California is there evidence or lack of evidence of connections between oil and gas development and protected groundwater resources? And why are the connections there if we see them? And is there any change in the groundwater quality adjacent to oil and gas development as a result of that development. This slide is a little bit busy, but let me walk you through it. And it's just going to give you some general timelines and approach that we do at every single field, and then how we have this whole program scheduled. We start off looking at all the historical data that's available. We look at water well logs, we look at oil well logs, we look at geology, hydrogeology, et cetera, in the area, and we come up with a synthesis that kind of gives us a picture of what's going on. And based on that, we develop site sampling criteria for both oil field fluids and groundwater. And then we go into more detail in data gathering. We look more in detail at geochemical logs, geophysical logs, excuse me. We actually go out and we sample wells. We analyze the data in the lab, and then we do QA/QC on it. And when appropriate, we then publish what we call data releases, which are our QA/QC'd reviewed products. And we publish them in ScienceBase, and at that point, they're available to the public at any point in time through their web. Then we start looking at the interpretive reports, where we synthesize that information in a spatial and topical context. We undertake a preliminary scientific review, and then we are here today presenting these preliminary results in public meetings. And then following that, we go through our final publication process and our final peer review to make that happen. You're not supposed to see the words in this square here in this diagram. Well, what I want to emphasize is that we stagger all this work for every oil field. So we started working in Fruitvale and Lost Hills, and then we start working in the next set. And it's this arrow shows you where we are today in terms of the work that we've done and where we're headed, very briefly. To show you that in a spatial map, we chose these two study areas to start with, Fruitvale and then the Lost Hills, North and South Belridge areas, for several reasons. We did a prioritization of all the oil fields in the state and came up with about 100. If you'll recall, that we rated as kind of top priority to take a look at. And Kern County is ground central for looking at these oil and gas and groundwater interactions, so we started there. And we picked fields on the east side and on the west side of the valley because we knew that they were in different hydrogeological contexts. And also because of the density of oil and gas development activities going on there. The next set we started on we're continuing on the west side of the San Joaquin Valley, going down from Lost Hills to the Belridges to Elk Hills and North Coast Levee, and then we expanded so some of the fields out in the coast areas, Orcutt, Oxnard, and Montebello. And this is, I think it's on paper somewhere, Karen, so you don't have to write the web address down, but all of the publications and documents are available online. They're listed on both the State Board and USGS websites. It's on the agenda, so you don't have to scribble that down. And the information on those websites includes the programmatic descriptions, what we're doing. It includes our sampling protocols, our QA/QC procedures, et cetera. It includes a list of our published reports and our abstracts and our published data releases. This is also in paper in the back, so I won't go through it. I do want to mention that the regional monitoring program is targeted to use existing infrastructure and existing wells. And in some cases, though, we need new wells, new infrastructure where there's critical information gaps. In Fruitvale, our analysis showed that there's very limited effects of oil and gas development on the local groundwater systems, and that drilling a new well, which costs between $1 and $2 million, probably isn't warranted. But on the west side of the San Joaquin Valley, there's some very critical information gaps. And so we have and are in the process of installing 2 monitoring wells adjacent to Lost Hills and Belridge. some of the benefits that we hope to gain through those wells are we'll be able to really clearly sample the groundwater quality at known intervals at multiple depths. We'll also be able to very clearly ground truth some of our geophysical information at those locations and collect lithology data. We'll also be able to use those points as specific positions in any hydrostratigraphic units, and maybe most importantly, look at vertical flow directions. Over time, we'll hope to monitor water levels in these wells, as well as look at changes in salinity and temperature at those locations. So if you can see here, here are the locations of those two wells. The Lost Hills well was completed in the March-April timeframe, and you can see our geophysical log just on the right for that well. It goes down to 1860 feet, and we have 5 monitoring wells installed in one system, going through different levels of the Tulare and in the alluvium. And this red star to the east of the north-south Belridge area is our planned site where we'll be drilling within the next few weeks or so. And with that, I am going to turn it over to Jan. Wendy?
Okay, my name's Jan Gillespie, and my job here, at least in the Lost Hills Belridge area, is to introduce you a little bit to the Tulare Aquifer and maybe lesser to the overlying alluvium, because those are the 2 zones most likely to have protected water in them. We're going to be, let me start my slideshow on here so I can see where I'm at. We're going to be looking at the Lost Hills Belridge fields, which are, does this, there it is. Thank you.
If I could remind people online, if you have questions, to email them to us. It's in the appointment that was sent out.
So can I point to them with my cursor as well? There it is. Okay, now I'm looking in the right place. Okay, we're going to be looking at the Lost Hills and Belridge oil fields, which are showing up over here in red. This is Lost Hills to the northeast. We have North and South Belridge just to the southwest of that. These fields are in northwestern Kern County. Kern County is shown here in gray, and they sit about 40 miles to the northwest of Bakersfield. This whole area is in the very southern part of the Central Valley called the San Joaquin, so we're right in here. And this is an area that has most of the oil production in the state of California. These are big oil fields. They are not advancing. At all. Sure, I'm not supposed to have this pink bar here. Thanks, Wendy. Okay, these are really big oil fields. California is one of the largest oil producing states in the US, usually third or fourth. So these are production curves for those oil fields. You can see them here. Lost Hills is up here on the top. Belridge, both south and north combined, are on the bottom. South Belridge is the third largest oil field in California in terms of oil production. Lost Hills is the sixth. So these contain a lot of oil. On these curves, you can see oil production on the y-axis and year along the x-axis going from 1931 to about 2009. The green curve on here shows oil production. The bright blue curve shows water production. The light blue curve is water injection or steam injection. And the gray curve is water disposal injection. And I've also put on here for you the start of some of the various oil field activities here. Injection started in these two fields about the early 1950s. Water disposal started in the late 60s, early 70s. Steam injection, by the way, also started in the 60s. And hydrofracking began in about the late 70s and has gotten more frequent as time has gone on, and we've developed some of the diatomite intervals in these fields. Diatomite has very high porosity, very low permeability. So to connect the producing zones up, fracking is necessary. Okay, we're going to talk a little bit about the geology of these fields. Since I'm the first speaker, not only do I get to deal with the technical issues associated with the slides progressing, but I also get to tell you a little bit about the geology of the oil fields and set it up for the rest of the speakers. So we're going to look at the two fields here. Both of these are on northwest trending anticlines. For those of you who aren't oil field geologists, these are where the layers are arched upwards, so the oil tends to flow up to the top and be trapped in those anticlines. So we're going to look over here in these fields, as soon as I find my cursor, at a couple of cross sections or slices through these anticlines. One's here in Lost Hills, one's here in South Belridge on the next slide. This is a strat column of the San Joaquin Valley, and it goes much deeper than we need it to, but this is the eastern side of the valley. We're working over here on the western side of the valley, and we're just going to be working with these uppermost formations here in this talk. This top one that's shown in sort of a dark color is the Tulare Formation. We're going to spend a lot of our time on that. It's colored this dark color because it's a non-marine formation. It was laid down in freshwater environments, things like rivers and lakes. Below that, we have the San Joaquin. Find my cursor again. It's hard to see from over here. The San Joaquin, the Echegoan, the Reef Ridge, and the upper part of the Monterey. These are marine formations, so most of the water inside these zones were originally seawater. So they tend to be much saltier than the Tulare, and as a result, the Tulare is of most interest to us in terms of what is and isn't protected water. Over here on the cross sections, this is our section through Lost Hills. You can see the structure of the anticline, how it's arched upwards. These stippled zones right in here are producing zones within the Echegoan Formation. In the northern part of Lost Hills, there's also some production in the Tulare Formation, which I've highlighted in here. In South Belridge, we have a lot of production in the Tulare Formation. You can see it right down here in these lower zones inside my shaded area. There's production in the lower Tulare. There's also production from diatomite in the Echegoan Formation that sits right below the Tulare. Some of the conclusions I hope you come away with today, and we're going to discuss this, is we're going to look at the structure of the aquifer, mainly the Tulare. We noticed from our mapping that the Tulare is thinnest in the northwest, and it thickens off to the southeast and to the east. It has several layers in it that are confining in some areas, but not in others. The entire Tulare is not saturated with protected water. Even where it's thickest, only the upper part is saturated with protected water. Protected water in this case is called USDW, or underground source of drinking water, and it's defined as 10,000 parts per million total dissolved solids. We've used logs, geophysical logs from oil wells, primarily to map the base of this protected water, and as best we can, we've used lab analysis of water from some of the producing oil wells in the area to try to constrain our log-generated map. Had a little bit of problems with this, as you'll see later, in that some fields don't have enough data, and in some fields there's a poor relationship between salinity and depth. And finally, in looking around to try to find out where the base of this protected water was or is, I saw some fairly enigmatic log signatures that in some cases turned out to be due to oil field activities, primarily in my case, water disposal. So we'll talk about that. So let's start out with getting to know our aquifer, in this case, the Tulare Formation and the overlying alluvium. So we'll talk about its thickness, stratigraphy, and some of the pressure relationships within it. This is a map that shows the thickness of the Tulare Formation and the overlying alluvium. Where it's orange up here, it's very thin. It's about 0 to 500 feet thick up in the northwest, but it gets as thick as about 4,000 feet way down here in the southeast. So it really thickens up out there. All these wells are the wells that I used to make this map, the different electric logs. You can see them on here speckled throughout. Each one of these squares is a square mile. The formation also thins over top of the producing anticlines and thickens in between them. This is a well log. We'll be seeing a lot more of these well logs before the day's over. The well log is coming from that big red dot on the map to the left. And right here, this is the log. It goes from just about to the surface all the way down to 2,500 feet down here. This upper couple hundred feet, about 300 feet, is alluvium. This is the gravels and clays that overlie the Tulare Formation. At the bottom of the alluvium is a gray zone. This is the Corcoran clay equivalent. Some of you have probably heard of the Corcoran clay. Sitting above that is a thick sand called the 22K sand. And then above that is a mixture of sands and clays. This curve right along here that's shaded in yellow, where it's yellow shows you the sands. Where it's not yellow is more of a clay zone. So right here, for instance, at 1,000 feet, this is the top of the Tulare right here. At 1,000 feet, we have a clay I call the mid-Tulare clay. At about 1,800 feet is the amnicola clay. About 2,200 feet is the DE clay. And the Tulare Formation base is at about 2,400 feet. This graph over here to the right is a graph of pressure in these sands versus depth in the same well. So this is the pressure across the top, and this is the depth down in this line. Each one of these blue dots is a pressure reading within one of the sands of the formation. So in this case, at 800 feet, the pressure is about 200 psi. And as long as these points fall on a straight line, which I've shown here by these red lines that go through the blue points, we say that that is probably within a particular aquifer. Where we see them jog off, like right here across this clay layer, and start to fall on a different diagonal line, this would indicate that this clay is a confining layer of some type. So it's separating this upper aquifer from this lower aquifer. We see a little bit of offset down here, a little offset below the amnicola clay, and some below the DE clay in this well. My question was, how consistent are these confining layers throughout the study area? So I looked at a few of these graphs. This is the one on the left here. There it is. The one on the left here, where my cursor seems to have now found itself, is the well we just looked at. And I also looked at two other wells as we go to the northeast. This one here, and then one near the south end of Lost Hills, this one. And if you notice, as we go to the northeast, these wells seem to lie on more or less the same line, indicating that the confining ability of the clays seems to have diminished as we go up to the northeast. So we're not sure that these are going to act as regional confining layers, but maybe of more local extent. Just to give you an idea of a map of some of these clays, this is a map of the elevation of the top of the Corcoran clay in the study area. Where you see it in green, it's below sea level. Where you see it in yellow, it's above sea level. And where you see it shaded in gray is where it's absent. So in those areas, we can't count on the Corcoran to be in between the alluvium and the Tulare. This is the new well that we drilled in Lost Hills over the summer. It sits right here. And in it, you can see these are the cuttings from the well at 20-foot intervals, 0 to 20, 20 to 40. And right down here at about 280 to 300 feet is where the Corcoran starts. You can see the change from the orange color to the gray. So we did find the Corcoran in that well. This is a map of a deeper clay, the amnicola. It's very it's very deep down here, very low elevation, and gets higher elevation up here on the structure. And again, it's absent over here in the west. We found that in the new well also. We found these little tiny amnicola that are about a few millimeters across. And so we were able to see, we're right on the feather edge of that, but it was present in the new well. Now, once we've characterized the aquifer, the really important thing to do is figure out what part of this aquifer needs to be protected and monitored. And that was the real goal of this whole, my part of this whole study. And so I wanted to map the aquifer salinity, and I did it in two ways: log analysis and then lab analysis, chemical lab analysis. So let's look at the logs first. And I know that some of you probably don't work for an oil company and don't know a whole lot about logs. So I'm going to give you a really fast primer. When we drill a well, and there's like 140,000 wells in Kern County, and most of them have geophysical logs, especially electrical logs. When we drill these wells, before we line the hole with steel pipe, we run a tool down the hole from the back of a truck. There I am. We drop it to the bottom of the hole, we pull it up, and we take measurements as we move up the hole. One of the most important measurements we take from this perspective is we measure the resistance of the formation to an electrical current. As it turns out, salt water is less resistive to an electrical current than fresh water is. So using this information, we can make assumptions, and pretty good assumptions, about what the salinity is in that aquifer. So let's look at one of these logs, and I'll just run you through it. This is a log from one of those wells. It's an electrical log. It starts at about 500 feet up here, goes down to 900 feet, continues over here from 900 to 1,300 feet. And this is the resistivity curve from the log. It goes from 0 to 20. And where the resistivity is higher, so you see more yellow shaded on the curve, we have fresher waters. It provides higher resistivity to the current. I've shaded this at about 3 ohms. So anything greater than 3 ohm meters shows up. As we go deeper into the hole, we see the yellow color disappear, meaning the resistance to the current is lower, and so we have more saline water in that zone. We take those values and we plug them into an equation that's been used in the oil industry for years called Archie's equation. And this value, R0, is the value you read from the logs. You multiply that by the porosity of the formation and some of these Archie's coefficients that come, in this case, from special core analysis that was done in the field. And it gives you the resistivity of the water in the formation. By knowing the temperature, I can convert that to salinity with respect to sodium chloride. And you can see that I've done that here, 2,900 milligrams per liter at about 550 feet. 2,600 down here, 2,750 here, 4,800 down here at about 800 feet. So right here is base of fresh water. Somewhere in here at about 750 feet is what we had been protecting in the past, water less than 3,000 parts per million. So I'm still not at 10,000 parts per million, so I'm still in protected water at this depth. If I go down, I see 5,000 parts per million, 7,600, 9,000, 12,500 at a depth of about 1,200 feet. So I know that my USDW, my base of protected water, is lying in here at about 1,175, 1,150 feet. And so that's what I was going to use to map the depth of protected water. Now, one thing about this procedure, I can't use it in any wells that have oil or gas in them because oil and gas impede the current, the flow of the current as well. So I had to stay away from that. So all of the wells you see on this map were wells that we found with core, mud log, or driller log data that showed oil, or they were completed. And so I had to stay away from any of these areas where you see a lot of this green. So mostly I'm working outside the fields or maybe here in South Lost Hills where I'm below the oil-water contact in the Tulare. I found 29 wells that I was able to use to calculate the base of USDW using the logs, and those wells are shown here on this map. And the red colors right here are places where the base of fresh water is 600 or less feet deep. Where it changes from yellow to green, I'm at 1,000 feet deep. Where it changes from blue to purple, I'm at 1,500 feet deep. So you can see that the depth to the base of fresh water is getting deeper as I move to the southeast. It's already also getting deeper really quickly from the top of the Lost Hills anticline out into the out into the areas to the east flank. In fact, we're at 1,800 feet deep to the base of fresh water at less than a mile outside the oil fields. One of the things I wanted to do with this is, because this is all calculated from logs, I wanted to compare it to chemical analyses to see if this was a valid way to do this. So most of the information I have in terms of chemical analysis comes from the Dogger geochemical database, and they're producing water along with the oil. They're taking that water, sending it to the lab, and having it analyzed for major ions for the most part, and then I get a TDS value from that, total dissolved solids. Unfortunately, most of this data is coming from producing oil wells, and of course with my log analysis, I can't use producing oil wells to do this. I have to look for wet wells. So it's not quite apples and oranges, but maybe two different kinds of apples. And this is a diagram. This is North Belridge. I only have one sample from North Belridge. This shows salinity on this side, and this axis is depth on this side. And right here I have this red line is 10,000 parts per million. So any sample that falls below this red line would be considered protected groundwater, presuming it's not exempted because it comes from an oil producing reservoir. And in most cases, these samples do come from that. In this case, my one sample says at 500 feet, I have a value of 6,000 parts per million. So it is considered protected. Unfortunately, I can't draw a straight line through one point. It doesn't work that way. So all I can say is that that well, which is right here, my map says the base of fresh water should be at 900 feet. This says, well, I don't know where the base of fresh water is, but I can tell you that at 500 feet, you're protected. So, okay, I'll take it. South Belridge has a lot more data because there's a lot of production from the Tulare. I actually split South Belridge into a northern and southern part right here. Here's this red line. So I put all the samples from northern South Belridge in one group and from southern South Belridge in another. One of the things you can see from this particular graph is that I don't have the world's greatest relationship of salinity with depth. On the east side, this worked great. West side, not so much. One thing I can do with it, though, is I can say that below about 1,200 feet, I really don't have any more protected water. No more samples falling below this red line. So if I go over here to my map, I can see here I've got 1,100 feet, 1,100 feet, 1,200 feet, 1,300 feet, and then back to 1,200 feet. So it's showing me, my log-generated map is showing me about 1,200 feet. In southern South Belridge, I have fewer samples, and they also have abysmal relationships between salinity and depth. But I do have this one well down here that was sampled at various intervals with depth. And the sample here at 1,500 feet was protected water. At 1,600 feet, it was greater than 10,000 parts per million. So I know that I'm probably about 1,550 feet to the depth of base of protected water. My map, there he is, my map shows it to be about 1,400, 1,500 feet. So I'm a little bit shallower on my map than the chemical data would indicate, but not too bad. Finally, we get to Lost Hills. And on Lost Hills, I've got two different sets of dots for you to look at, now that you're so good at this. The blue dots are from the Tulare Formation, and the red dots are from the underlying Etchegoin Formation. The Etchegoin normally we don't consider as being protected water out here because it was deposited in an ocean. So typically we see, there he is, typically we see that we're up here at around 30,000 parts per million total dissolved solids. We're looking at old seawater in the Etchegoin. But in northern Lost Hills, we actually see a couple of protected samples in the Etchegoin. And I think that what's going on here is that here the Etchegoin and the Tulare are right on top of each other, and the sands may be in communication with one another. So we have fresher water from the Tulare seeping down into the Etchegoin. We also have a steam flood going on here in the zone. So that means we're injecting fairly fresh water into this area in the form of steam, and that's diluting the seawater that was present originally in the Etchegoin. What we can see here is I only have in the Tulare, in the blue, I only have one dot from this well right there that shows unprotected water, and that's at a depth of about 1,000 feet. So my chemistry is telling me that depth to protected water here is about 1,000 feet. And if we look at the map, this change from yellow to green is 1,000 feet. So that's this well right here. On my log map, it's lying right on 1,000 feet. So it makes me fairly happy with how the log data is working out. Okay, lastly, I want to talk about oil field effects on salinity. And as I was going through this data, trying to figure out where the base of protected water was, I started seeing anomalies. And I started to look at those and try to figure out why they were there. In some places, the saline water was showing up much shallower than I thought it should. When we look at production in an oil field, and these graphs have water-oil ratio on the y-axis, so that's how many barrels of water do we pull up for each barrel of oil we bring up. It's got years down here on the x-axis from 1931 to 2010. And Lost Hills was actually discovered in 1910, Bell Ridge in 1911. And when we first discover an oil field, we take out almost complete oil with just a little bit of water. But as we continue to take this oil out and sell it and ship it off, water often comes in to take its place. Either water that comes in naturally from the aquifer, or maybe water that was introduced as part of water flooding or steam flooding. So over time, the water-oil ratio starts to increase. So for instance, down here at Bell Ridge, you can see there was almost no oil or water being produced along with that oil. By 2010 or 2016, we had 14 barrels of water coming up for every barrel of oil. At Lost Hills, we had 12 barrels of water coming up for every barrel of oil. And that oil or that water has to go someplace. It's not of the quality that we would like to see used for irrigation unless we clean it up. Nobody's going to want to drink this water. It's pretty salty. So what people have done is dispose of it over time. Historically, the way it was done was to run down unlined gullies or be placed in unlined ponds up at the surface and then be allowed to evaporate or percolate downward. And all these ponds are shown here in sort of a turquoise color on the map. And what I wanted to do was call your attention to this cluster of 3 wells that I have circled in red. These wells were drilled at different times, and they're practically right on top of one another. So we can actually see snapshots of changes in aquifer quality through time by looking at these wells. So over here on the right, this is the oldest well of the group. This is from 1970. And this log goes from about 0 to about 500 feet deep. All of these logs do. And if you listened closely to my little lecture on how to read electric logs, you would say, wow, this upper part in 1970 had some really fresh water in. The resistivity is really high. And not knowing anything else, you'd be right. But actually, in this case, those sands are full of air, and air also doesn't conduct a current. This is above the water table. So the water table back in 1970 in this area was at about 300 feet. So we're looking above the water table and below, and we still have some shading below the water table. This is the 22K sand, this is the Corcoran clay, and this is the Tulare Formation. By 1986, 16 years later, we see that all this high resistivity is gone in this well. It's been replaced by very low resistivity that I've indicated with this pink bar. And the water table now, instead of being at 300 feet, is at 110 feet, so it's gone up. And all this has been filled up by very low resistivity salt water percolating from the ponds. By 2012, the water table has climbed to 90 feet deep, and we still see this very low resistivity interval right here. We also are now starting to see low resistivity down here in the 22K sand. Right here you notice that it was yellow in these wells, but now it's not anymore. It's very low. It's full of salt water as well. Fortunately, the Corcoran seems to be protecting this lower aquifer, the Tulare aquifer, from most of this percolated water. These are the wells that I've looked at and think I may have seen evidence of pond effects. I'm not as sure about the wells in Lost Hills, because Lost Hills traditionally up here in the northwest of the field has had very saline water. There was Tulare Lake was up there during the Ice Age, and as it would evaporate, it would leave salts in the soil that would then be flushed down to the water table. So I'm not sure that what I'm seeing at Lost Hills is coming from the ponds. This stuff I'm pretty sure is farther south. The other way we've disposed of water is by water disposal wells. In the 1980s, they started to phase out the ponds and put this stuff into water disposal wells, in some cases in the Tulare Formation. So this is a slide from Tracy Davis, who will be talking later, and we can see that, there he is, in Lost Hills, we had about 300 million barrels disposed of into these wells in the Tulare and Echegoan Formation. Most of these Tulare wells have been phased out now. In the southern end of Lost Hills, we had about 419 million barrels disposed of. Maybe one of these wells is still active, most are done. A little bit of disposal in the Tulare and alluvium at North Bell Ridge. Again, most of those wells are not active anymore, but quite a few are active here in the Tulare Formation at South Bell Ridge, where they've injected about 1.4 billion barrels of produced water. I want to call your attention to two wells right here. They're two disposal wells near South Bell Ridge. And again, we'll look at changes over time. This is the older of the two wells. This is 500 feet. The Corcoran clay is up above this well log right here. And so we go from about 500 feet down to about 1,000 feet in each of these wells. This is the older well. This is from 1990. You can see the resistivities are fairly high, getting lower as we go deeper, which is common. But if you look in 2012, we can see that it looks like there's been big bites taken out of the resistivity in here. It's gotten very low here, here. This seems fairly unaffected, but we've got some here, here, all these little things that look like bites taken out of the resistivity. These are probably due to the disposal of the saline produced water injected into these producing or the disposal wells over time. And these are the areas highlighted in pink where I think I've seen evidence of that in the study area. So to conclude, I want to mention that we've seen that the Tulare Aquifer thickens from the northwest to the southeast, from about 250 feet in North Lost Hills to about 4,000 feet. It thins in the oil fields as well. It contains individual aquifers shown by pressure data. These don't seem to be of regional extent, but we do see effects of them locally by looking at pressure changes and in some cases salinity changes. The base to depth of protected water also slopes to the southeast from about 500 feet in North Lost Hills to about 1,600 feet down near South Bell Ridge, and it thickens really fast. It gets really deep as we go from North Lost Hills to about a mile east of the field boundary. The lab analyses have helped with my log analysis maps for depth of protected water, but they are a little bit sketchy because they don't follow the depth and salinity relationships in the samples aren't good, or I don't have enough of them. They're also from oil wells rather than water wells. And then finally, oops, I missed a bullet. We've seen high salinities in the alluvial aquifer above the Corcoran clay, or sorry, high salinities, low resistivities, caused by percolation of salt water from these old sumps, these old disposal ponds. We also see some intervals of low resistivity, high salinity within the Tulare Formation due to water disposal in some of the injection wells. And that's it. So do we have time for questions or do you wait? Okay.
Hi, Catherine Moore. I'm at the Senate Natural Resources and Water Committee. Could you go back to the slide which showed the data points that were showing the pressure discontinuities towards the beginning?
This one?
The next one. Do you see it looks like there's a little bit of a discontinuity about like 1,300 feet or 1,500 feet. I mean,
yeah, right down here below the DE clay.
Well, between the DE and the M Nicola, but also below the DE. What's
right,
that?
Right here, definitely. Yeah, and that one, they did do some injection here, but yeah, this is definitely a separate aquifer across this. Mm-hmm.
Oh, sure.
So we still see that.
But even within just between the M. Nicola clay and the DE clay on the middle one, it looks like there's sort of two groups of data. I mean, is that a real difference?
Yep, that's a real difference. So this very lower 200 feet of the Tulare seems to be acting as a separate aquifer.
Okay,
You're right.
thank you.
Any other questions?
Sure.
Okay. Too slow. It's okay.
Sorry, Will Stringfeld, Lawrence Berkeley Lab. Just on the ponds that are showing impact, do you have any idea how wide a zone that is of impact?
Actually, this lady standing up here right now may be able to answer that question better than I can. My data is very limited outside the limits of the oil field, but Lindsay here, who's going to speak next, has been flying over the areas that I can't see due to lack of well data. So I'm not sure how to answer your question, but she may be able to do that better than me.
Maybe hang on to that question until
Yeah.
I go through my slides.
It's a good lead-in question for Lindsay. If I can figure out how to close out of this. My cursor's...
Oh, I'll figure it out.
I am so
Or Wendy
feeble
can
with this
figure
thing
it out.
today.
That would, let's try. All right. I'm Lindsay Ball. I am a geophysicist with the USGS based out of Denver. We've been working with airborne electromagnetic methods to supplement the salinity mapping in the groundwater areas. I'm going to speak today specifically about the Lost Hills and Bell Ridge survey area where we flew in 2016. And I'm lucky that Jan gave a fantastic overview of the geology of the region and the background hydrostratigraphy, so I'm just going to assume everybody is on board with all of that. We're going to go through a brief overview of the salinity mapping objectives from the Airborne Geophysical Survey. We're going to look at qualitative interpretations first, looking at patterns in resistivity that we observe from the survey and what that may mean for relative water quality. And then we're going to do a brief overview of the quantitative process where we quantify uncertainty and mapping salinity throughout the study area in 3 dimensions. So as Jan showed, we're working on the west side of the San Joaquin Valley. If I can track where we're going over here on the side. So we're looking specifically again at this Lost Hills and the north and south Bell Ridge area along the west side. The airborne electromagnetic method fundamentally maps resistivity of the subsurface. So this is very similar to what Jan was talking about conceptually with borehole methods, and also what you may be familiar with from surface methods such as electromagnetic soundings or profiling. The difference is that we are able to suspend sensors from an airborne platform. So if you were in the Central Valley recently and have seen some of these surveys going on, it's kind of a strange sight to see. It's a giant hula hoop. It's about 15 meters on a side. That flies at a very low elevation, about 100 feet off deck. So it is definitely notable when it happens. But being able to move to an airborne platform, what we're able to do is we're able to map continuously over a large area, both in high resolution and at a regional scale. So as opposed to looking at highly detailed information in boreholes, we're looking at slightly less detailed information, but in a regionally extensive area. This allows us to map the changes between wells or between borehole geophysical logs where we have a really detailed understanding about what we're seeing, and look at the way those conditions where we can measure them in wells changes over space between sample points where we may not otherwise be able to see. This allows us to make a much better regional interpretation of how things change over space, and also gives us an ability again to upscale to that regional scale.
Specific objectives of our geophysical mapping effort were to look at protected water adjacent to high priority fields in the San Joaquin Valley, and specifically Lost Hills and North and South Belridge, and also to support the development of improved hydrogeologic frameworks. These methods really help us map hydrostratigraphy and geologic structures, so they can help us put our results in a better hydrogeologic context than we might be able to do from the well logs alone. The airborne EM survey near Lost Hills was flown in October of 2016, so everything that I'll show you today is essentially a snapshot in time, and there is a lot of transience in the conditions out here, so it is important to keep in mind that this really is an October 2016 timeframe. Total survey distance was roughly 1,440 kilometers, or about 900 miles linear distance. Those are flown in a series of parallel flight lines, as you see in the map here. The distance between these lines, where they're most far spaced in the block, are 300 meters. The more closely spaced lines are 150 meters between flight lines, so about 1,000 feet is our typical spacing between flight lines. Along the flight lines, we tend to have, in the end, a sample data density of around 30 meters. So about every 100 feet, we resolve a data point that we're able to use for our mapping effort. We flew this with a SkyTem 312 system, which is one of the airborne electromagnetic systems that are available commercially. So that is a commercial company. This is one of the bigger systems. I would call it a large hammer. So it's really trying to get about as deep as you can get for the conditions in the area. Before I get into any of the nitty-gritty, just a couple bookkeeping items to make sure we're all on the same page. For the geologic framework, I'm going to talk a lot about the Corcoran clay equivalent. That's the same surface that Jan was mapping. In general, I'm going to say anything above that we'll just call alluvium. And I know sometimes a lot of people consider the Corcoran clay is in the middle of the Tulare, but just for the purposes of being clear, if I call it alluvium, I'm really just saying it's above that Corcoran clay equivalent. If it's below the Corcoran clay equivalent, we'll call it Tulare. Other geologic units that are in the study area are typically below the airborne EM depth of investigation, with the exception of the Belridge diatomite, and we'll see a little bit of that. But typically, we're only seeing about the upper 600 to 1,000 feet, given the conductivity of the area. So we don't typically get down into the Etchegoan or the deeper formations. For salinity, I know one man's fresh water is not the same as every man's fresh water. For saline water, we'll use anything above 10,000 milligrams per liter. Anything between 10,000 and 3,000 milligrams per liter, I'll call brackish. And anything fresher than 3,000, we'll call fresh. And then most importantly, the fun part of the rainbows, for the geophysics, because we're looking at a regional scale and we're looking a lot at continuous data, we won't be looking at line plots like Jan was showing you. We'll be changing all of that information over into color scales of relative resistivity. So what you'll see in the color scales in the various graphs that I show you will show you things that are pink or red will be on the saline side or the more conductive side. Things that are going to be to the greens and the blues are going to be fresher water. There's going to be higher in resistivity. And as a geophysicist, I often will interchangeably use the word conductivity and resistivity together. It's just something we do. Those are just basic linear relationships. So if something's high resistivity, it's low conductivity. If something's high conductivity, it's low resistivity. I'm going to go ahead and start with the conclusions up front. So if you don't want to hear any of the details, you can totally zone out after that. The general resistivity patterns qualitatively indicate that the Corcoran clay equivalent is an effective regional confining unit. Additional clay units also locally control groundwater flow and may stratify water quality, and we'll look at examples of that. Saline and brackish water is common in the alluvial aquifers. Fresher water can often occur below that more saline water, so it's not a simple mapping to a depth of a saline interface. It can become saline and then become fresher below. Relative fresh water occurs in the Tulare aquifer adjacent to the Belridge fields. Things tend to be more conductive and likely more saline adjacent to the Lost Hills field, particularly in the Tulare aquifer. Unlined canals and the Kern River floodplain serve as an important freshwater recharge source, and we'll show the regional patterns associated with that. And resistivity patterns are consistent with other groundwater salinity observations and provide spatial context for these samples. So everything that I'm going to show you today is not really that different than what you can see in water quality samples. It's really very consistent and very well correlated, where we're looking at the spatial patterns between those known points. Okay, so the fun stuff begins. And hopefully you can see the bouncing red ball here. So first we're going to look at the geologic framework as we see it in the resistivity section. That's the panel that you see in the middle. This is just like a cross-section that you'd see into the ground. The location is highlighted in red on the site map. So you've got the North Belridge field here, South Belridge Field down here. And we're looking at this red line, which is going to be out in the groundwater flow area. So we're not working inside the oil and gas perimeter necessarily where it's developed. We're really just looking in these agricultural regions. This section is a cross-section along that line. So in this case, it's going to go from south to north. Sorry about that. So South Belridge Field is going to be down here, going to Lost Hills to the north. Over here, this is the field boundary that you can see in the map. What we see in the cross-section, which has elevation on the y-axis and then distance along line on the x-axis, is a series of fairly clearly defined resistivity layers. We've got what we'll call a bluite, this relatively high resistivity layer that's blue at the very near surface. There's consistently this red unit, this red and pink layer. This is high conductivity, low resistivity. Below that, we often see a transition into a more resistive subsurface. Between those two positions, I would typically interpret the Corcoran clay equivalent to happen. I'm doing that for a series of reasons. One, we have a lot of independent ground truth on the location of that clay. That's provided from monitoring well records and also from independent borehole log analyses that Jan Gillespie has given to me. When we look at those independent ground truth points, what we often see is that the base of that conductive unit, basically where this black line is drawn, is where the top of the Corcoran clay is typically mapped. So the red unit is not the clay unit itself, it's material sitting on top of that clay unit, and that's also well correlated to saline water well records from monitoring well data. So these gray lines that you see here, I'm sorry, they're quite hard to see because the well screens are quite narrow, are color-coded at the well screens that show you the water quality category, saline, fresh, and brackish, associated with that well. You can also see those categories, although not with depth, down in the map below. So you can see that you have a pink point here that's related to a hit on a saline well, another one there, and here's a relatively fresh well here that happens to be screened below the Corcoran clay. So what we see is that this relatively spatially consistent pink unit is well correlated to that saline water that we find in well data. The Corcoran clay appears to be pretty effective at keeping that from flowing into the lower Tulare aquifer. We also see a strong spatial correlation to historic produced waters ponds. In this case, the Lost Hills Pond is the boundary that you can see here. The cross-section above is showing you a groundwater monitoring report with a conceptual cross-section drawn that also shows some of those well locations. What you can see is, and this is something we consistently see, these conceptual diagrams are really good. They're really well drawn, and they do a really nice job of agreeing with the airborne electromagnetic data. So you can see here they've conceptualized leakage coming out of the Lost Hills Pond, going down to the Corcoran clay, and then flowing along that surface. We also see that depression in the Corcoran clay, that relative dip, and we also see the continuity of that produced water sitting on that material, or on the clay unit there. You can also see a nice correlation to the surface of the Lost Hills Pond. So that helps us build confidence that what we're really seeing in the geophysical data is water quality contrasts being controlled by the geologic framework, not necessarily differences in the geologic framework itself. Using the information that we've gained from being able to map the Corcoran clay using these electrical contrasts, we did a refinement of the Corcoran clay equivalent surface. This helps us understand hydrogeologic controls on produced water that may be located in the alluvial aquifer and also general salinity patterns that we see in the alluvial aquifer. This is based on the data that Jan provided me from her borehole pics, and we extend much more resolution in that information going into the airborne electromagnetic survey where we can correlate those points. We also, at the regional scale, use published Corcoran clay data to try to tie into the regional structure so that this map is consistent with what's been regionally mapped before where we don't have specific data. In this case, this is mostly coming from the Page 1986 water supply paper. What you can see in the Corcoran clay map is that it's pretty steeply dipping in the north, less so over the North and South Belridge fields. A couple of things to highlight that are hydrologically significant. While the Corcoran clay is a regionally significant unit, there are other clay units in the area that we see contrasts with that probably also locally control groundwater salinity. In this case, looking adjacent to the Lost Hills field, this is a cross-section that goes from the west to the east along the highlighted black line. The black line that you see in the section is where we'd estimate the Corcoran clay to be based on Jan's pics where we're at the field, and then following out with the context that we have. You can also see that there's a lot of internal stratification in the relative resistivity structure. And that's probably in part water quality differentiation among shallower clay units that are above the Corcoran clay that are still significant, but maybe not regionally continuous. They come and they go, but they are locally important. You can see that as well going over the top of the Bell Ridge diatomite to the south. So here we have another cross-section going from west to east again. This really strong conductive unit is what I'd call kind of a beacon in the night, which is what the Bell Ridge diatomite is. That puppy is well under 1 ohm meter. I love working with low-hanging fruit, and that one's really easy to find. When you can see coming across the top of it, here's an example of a clay unit that may be stratifying water quality that's not continuous over the top of the surface, one above it that maybe is continuous over the top of the surface. So we see a lot of interfingering of these different layers locally that may have some significance. Also apparent is a potential paleo valley that's adjacent to the north and south Bell Ridge front. So you can see in the Corcoran clay map, this relative yellow section is a low point. And there's another high that kind of comes up as you go towards the northeast, which is the general direction of groundwater flow. And this may have some local significance for controlling the local direction of groundwater flow adjacent to the Bell Ridge fields. We're going to look at a couple of depth slices. These are basically maps of resistivity at a specific depth draped below the land surface. We're going to highlight a couple of different layers, and these layers are significant in part because they're the median depths at which I have some well data, so they give us a good opportunity to compare our information to known salinity observed in wells. And they also show some representative locations in the data set. So the shallowest, the 7 meter or about 25 feet, is generally in that shallow alluvium. This is often above the water table, which is where I would highlight that these blue areas are relative resistive areas. Those are probably vadose, not necessarily freshwater, but unsaturated areas that are closest to the field. As you go to the east, the water table tends to become shallower. And there are the potential for perching conditions. So this big bright pink layer that you see is a very conductive surface unit. We see this extensively down gradient of essentially the aqueduct. That's a combination of water table and maybe the addition of some irrigation. In the triangles, you see information from shallow piezometer data. This shows an estimated TDS concentration observed at 25 feet, which is the general depth at which these piezometers are screened. And what you can see are a lot of pink triangles that correspond well with this conductive unit that we see adjacent to the Lost Hills field. This is a relatively shallow unit. It's probably not related to the oil and gas activities going on in the Lost Hills field, but maybe either a natural or agricultural source of salinity. But that is well correlated with shallow data where we know that there tends to be greater than 10,000 parts per million water. If you go further down gradient and you get below the West Side Canal, which is an unlined structure, you tend to consistently see very blue features, very high resistivity sections that are correspondent with fresh water. This is also seen in the piezometer data in the very shallow near surface. So it's likely that that West Side Canal does have significant leakage, and that leakage has been a long-term source of recharge. I'll also draw your attention to some more localized features adjacent to, in particular, the South Bell Ridge field. You can see here's the Lost Hills field that we were looking at that previous section where we see that conductor comes up to the surface. You can see that in the map here as well. You can also see some other conductors at the surface associated with potentially some other produced waters ponds, which are going to be these black circles that are indicated on the map. If we step down into depth and we move to the 50-meter section, or roughly 160 feet, we tend to be below the water table at this point, still mostly in the alluvial aquifer. What you can see is that conductive signal that was near these infiltration ponds is stronger and more spatially consistent at depth. So as we get well down into the water table, you can see potentially high salinity water that correlates well back to those produced waters ponds into the subsurface. You can also see that there's some potential local control where that conductive water does not really go straight to the northeast, but tends to trend a little bit towards the southeast before going northeast. That may be associated with that paleo channel or that low in the Corcoran clay surface. That saline water wants to sink to that and then flows along that area. We still see that strong freshwater signal down gradient of the West Side Canal. It's the blue region there. As we get into the water table adjacent to the Lost Hills field, it tends to be elevated in salinity. There's not as much well data in those locations for us to correlate to. But we do see that elevated signature, highlighting again that that pink layer that was in the shallower slice is maybe a perched condition. As you look slightly farther to the east adjacent to Lost Hills, we're now into a greener, more resistive unit that may be fresher water. Going down to 150 meters, generally in the Tulare Aquifer, around 500 feet, we typically see that the resistivity in the subsurface is generally a little bit higher than we saw in the alluvial aquifer, indicating slightly fresher conditions. That's consistent with what we see in the well data, which are these blue spots here. These are mapped as relatively fresh water, less than 3,000 parts per million. We still see that recharge signal, so that's consistent to depth, adjacent to the west side canal and down gradient from there. We see that adjacent to the Lost Hills field, generally consistently through depth, we're now at a more conductive state, or it's generally higher salinity. And that very strong pink unit is my beacon in the night. That's the Bell Ridge diatomite, which is a very strong conductor, very saline water. This map shows you kind of an illustration, mostly of that freshwater recharge region, but in 3 dimensions. So in this case, we're looking at a section like we saw before with elevation on the y-axis, distance on the x. That's going to be correlated to this red line here, moving from west to east, which is also in the 3-dimensional plot going to be this flight line right here that you can see. You can see the continuity in the structure that we get between flight lines and gives you a little bit of a better idea of the breadth of the data that we have. In 3 dimensions, these blue features are the mapped produced waters ponds, and the black line indicates generally the location of that west side unlined canal. So what you can see is the consistency of that unlined canal feature. You can kind of see it's actually more of like a freshwater plume, essentially, that comes out of the canal, which you can also see in this section here. This is the exact canal intersection, so that's that freshwater signal coming off of there. You can see the continuity in the saline water sitting on top of this Corcoran clay, the fresher water below. Also worth noting, the aqueduct is generally not something we see a distinct signature for. I don't see the same types of recharge coming out of that as we tend to see out of the unlined canal structures. I'm just going to give a brief overview of how we're using the resistivity data, not just qualitatively, but also quantitatively, to develop maps of quantified salinity. And this is also how we account for uncertainty in our interpretations. The objective is really to create a methodology that can be completely reproducible without being inside my brain, necessarily, which is not a place you probably want to be. I won't belabor the method, and I'm happy to talk about it afterwards with anyone who wants any nitty-gritty details about it. Just to give an overview, this involves building a regional relationship between resistivity and salinity observations using local data, and that allows us both to quantify our interpretational uncertainty and also gets us away from having to use a petrophysical relationship like Archie's law. The approach that which Jan uses in the borehole logs takes advantage of other information that you can get from borehole logs, things about porosity, that we can't get in the airborne data because we can't sample that at the same time. So by using local relationships, we're really divorcing ourselves from those specific relationships that require information about other properties and really looking just about the correlations between resistivity and salinity locally that we can observe. This also helps us avoid things like changes in clay content, which also affect resistivity, but aren't related to salinity. That'll all be accounted for inside of the analysis. We apply that regional relationship to the airborne electromagnetic data, and that allows us to quantify our geophysical uncertainty. The result gives us maps of categorical salinity conditions, and again, this is fall 2016 only. Both the alluvial and Tulare aquifers, you'll see, have regions of fresh and saline to brackish water. And our higher confidence generally is above the Corcoran clay unit, but we're typically able to work up to depths of 1,000 feet. Just give you a brief understanding of the regionalized resistivity to salinity category. Essentially what we're doing is taking known wells where we have either recent or stable water quality data, and we look at the resistivity as measured from the airborne electromagnetic system at those points. So we have a place where we know what the salinity is, and we ask ourselves, well, what is the resistivity, and what is the distribution of how often resistivity is that same value in other places? So that gives us a series of distributions for categories. We're working in a fresh, less than 3,000 parts per million category, brackish between 3 and 10, and saline greater than 10. What the map on the right, or I'm sorry, on the left is showing you is the relative frequency and that resistivity distribution. So these are just distribution functions or histograms showing you those data. And what you can see is that the saline and the brackish water, that's the pink and the green section here, Those are pretty close relationships. They have some room between them, but they're really not super well defined, whereas the freshwater category is much more cleanly defined. And because of that, we're working in a 2-category system. I'll be mapping things that are saline and brackish versus things that are fresh, less than 3,000 parts per million. Another way to look at that is to look at this sort of cumulative viewpoint. What this is basically showing you is your probability of being in either of those 2 categories. So resistivity down here on the x-axis, this is very conductive, 0.10 meters, ranging to very resistive, 1,000 meters. What you can see is in the most conductive areas, using the relationship that's locally defined, we have 100% confidence if it's 0.10 meters, it's saline. There's no if, and, or but about it. As we get up to 1 meter, it's still generally very, very confidently saline. Very, very infrequently can you have a freshwater well that's going to show that level of conductivity. As you get to 2, 3, 4, 5, up to 10 meters, that's where you get into a gray area between those 2 categories, where sometimes freshwater wells have resistivities of those signatures, and sometimes they're more saline or brackish. That's a lower certainty area, and that kind of information gets pulled into our final analysis. So we own that uncertainty in the final interpretation and can quantify that. As we get above about 20 meters, we almost never see saline wells in these conditions. It's really not consistent for water to have that kind of salinity and for the conditions to be more resistive than that. So we have almost 100% confidence. If it's 20, 30 meters, it's not a saline water well. I'm going to skip over the geophysical part completely, and I'm happy to talk about that with anybody who'd like to know more about it. Basically, we use a stochastic approach, and that gives us an ability to look at our confidence at resistivity values, or how well we know something is 1 meter. That's compounded with our interpretational uncertainty from the last slide, and that allows us to make these maps of the likelihood of being in a category. So what this map shows you is a depth slice, just like the slices that we were seeing before. This is an example from the 50-meter depth. They're about 150 feet. The strength of the color shows you our level of confidence. So if something is very, very yellow, we're high confident, and something is very, very blue, we're high confident. If something is sitting around 0.5 or 50%, we're not quite sure which way it could be, and that could be based on the geophysical data or on the interpretational uncertainty. It could be that 3, 4, 5 meter range where it's hard to tell. If something is yellow, it's most likely to be saline, and if something is blue, it's most likely to be fresh. And again, the stronger the color, the more confident we are. And what you can see is this maps really well to the ground truth that we had. So you're seeing wells here again that are color-coded based on their salinity category, green, yellow, and blue. I'm sorry, pink, yellow, and blue. And what you can see is that to the east, down gradient of the West Side Canal, we have very high confidence in our ability to map that fresh water. It's a very strong blue color. The confidence tends to be relatively high, which means the resistivity is relatively high, and the data quality is also high. You can also see a relatively high confidence region of being relatively fresh in the South Belridge area. You can see the saline area following that paleo channel, likely associated with saline water in the alluvial aquifer. You can also see that relatively saline area, although slightly less confident, adjacent to Lost Hills. As we get up north of Lost Hills towards the northwest Lost Hills field, a little less confident, and that's why the colors are going to be a little more muted in that area. We go across the I-5, higher confidence that we have saline conditions that are probably natural sources of salinity. So these are the types of maps that we will have in publication, and these can be made at any depth slice and also fully in 3D. So in conclusion, we've shown that general resistivity patterns indicate the Corcoran clay is an effective regional confining unit. We tend to see those strong resistivity contrasts across that boundary, and it's well ground truth that the base of those contrasts tends to be the Corcoran clay. Saline and brackish water is common throughout the region. Freshwater can occur below the saline water. We see that in well data, and we can correlate that to the geophysics. Relatively fresh water likely occurs in the Tulare aquifer adjacent to the Belridge fields. Adjacent to Lost Hills, salinity tends to be a bit more elevated into the Tulare. Down gradient of the unlined canals in the Kern River floodplain, these are areas of likely freshwater recharge and also a great place to find fresh water. AEM interpretations are generally consistent with what we see in the geologic framework and with salinity observations. And the quantitative salinity mapping shows our confidence in defining salinity categories in 3D, both with respect to interpretational and geophysical data uncertainty. And with that, thanks for the attention, and I'd be happy to take any questions you might have.
Yep, we have 2 questions.
Okay.
One's from Andrew. He asks, are the findings from Jan and Lindsay's research consistent with the aquifer exemptions that have been issued for these oil fields with regards to salinity and zonal isolation? And the second part of his question is, could these methods and findings be used to corroborate the claims made in exemption applications?
So I am not familiar personally with the specific exemption applications. So I'm afraid I can't comment on individual exemption findings. That's outside of the published record. So I'm afraid I don't know. And I think that kind of takes care of both of those questions, unfortunately.
But I will say that Andrew should contact us and we can go through the very quantitative looking at this is the area outside of the areas that are exempted. And
That's
so
right.
we may not have really good correlations, but we can look at where the boundaries are.
Right. That may be more consistent with the information that Jan's been working on, which is inside the field boundaries.
And our second question's from Laura. There's a general question about wastewater pond info. There's a website that maybe you can look at afterwards to see if that correlates. I'm not going to bring that up now. But she also asked, could you measure the elements in the salt next?
So I'll have to direct that question to the groundwater chemistry talks that'll go on after this, where they'll look at specific sampling results that look at major ion chemistry. With the resistivity system, we're typically only looking at conductivity, which is related to total dissolved solids, and we can't really pick out any more detail than that.
Well, I'll start here. I'm right here, though.
Catherine Moore, Senate Natural Resources. Are these overflights going to be done again in the future?
So for the Lost Hills Belridge area, this flight is concluded. I'm not sure if we'll end up doing time-lapse surveys in the future. That's not been something that's been planned. We have continued on with surveying in new areas, specifically moving down into the Elk Hills area. That was flown in 2017, and we do plan on continuing to fly onto the south to complete the mapping along the western side of the San Joaquin.
Hi, this is Scott with the State Water Boards. Could you put up the first fun slide with a cross section?
I assume I know what you mean by fun.
The first fun slide.
That one.
Yeah, so the conclusion that the CCE is a barrier to 10,000 plus water, there's no data beneath the Lost Hill ponds there. So you have 10,000 plus and then a dashed line and then white. Is there any other data to support freshwater beneath that location?
So beneath that depression specifically, I'm not able to resolve below that unit because the conductivity of, especially at that thickness, kind of attenuates our signal essentially. It's hard for us to see below. There are water quality samples in monitoring wells that do go below the Corcoran clay in a lot of locations. I'm not sure specifically about this one. I think there are. I'd have to look about Lost Hills in particular. But typically we do see that there's fresher water below the Corcoran clay when it's been monitored.
Lindsay, while you're on that slide, could you explain in some of the deeper areas where you're 100 meters or so beneath the surface where you have Tulare Aquifer labeled on the cross-section, can you explain what's going on there where you have that red area?
So some of the red area that you see like below where the CCE is labeled, that's starting to nip into that Bell Ridge diatomite. So we know that to be a strongly saline area that's typically very conductive. The more conductive it is, the easier it is for us to see it at depth. The relatively yellow region is probably elevated salinity in the lower Tulare. The challenge there is that there are very few wells that go at that depth. A lot of the wells in these areas get below the Corcoran clay, they sample that fresher water, and they don't go deeper than that. So there's very few data points that get into these lower positions in the groundwater flow area to really ground truth the exact salinity in those locations. So we're relying on the relative salinities that we've seen in other places and would intuit that that's more saline water at depth. But so basically you have a saline water interface at the top, the Corcoran clay, fresher below that, and then it transitions, as you might expect, into more saline water.
Hold on.
Wait for the microphone.
So where the high salinity material moves away from the ponds along the CCE there, is that interpreted to be related to the ponds too? Or
So I would say it's easiest to tell that using geochemical data, being able to sample that. Spatially, it is correlated to the pond area, but there could potentially be other sources of salinity in the region. Let me see if I can pull up one of these maps that shows a bit more clearly. So what you do see is you tend to have somewhat elevated salinity in the surface, not quite as strongly as you see nearly adjacent to the ponds, but they do seem to extend out quite a distance.
I had another question on the last fund slide.
I have a harder time figuring out which
You
one's the last
mentioned
fund
it is
slide.
where you had,
Probably before the quantitative, right?
yeah, the
That one.
confidence, the map with your confidence. You had high confidence in the upper part of that figure. You had high confidence fresh blue and then high confidence saline yellow right next to each other. And you indicated the yellow there was maybe a natural feature. Is the idea that flushing from the canal has displaced naturally occurring salinity in that area, or is it just a geologic, a different lithology explaining that? I mean, it's interesting that you have such high confidence contrast there.
It's high confidence because it's extremely conductive. So that's a very strong conductivity signal. That is an area where water samples that exist do tend to show elevated TDS. So we're pretty confident that that is saline water. So the mapping effort does reflect that. The source being natural is in part because there's just very little development in that region across from the I-5. That's well away from the oil and gas fields, and it's not an area that's actively under irrigation as far as I can tell. So it is likely that that's some type of native salinity, and it's not unexpected that you would have elevated groundwater salinities of natural sources in these areas. The west side of the San Joaquin Valley is naturally a relatively saline region. So we expect to see a lot of elevated salinity in these aquifers that has no anthropogenic source.
So while people are thinking about maybe asking another question while you're thinking about it, I wanted to make an announcement to tell your friends in case they missed the meeting today that this is being recorded, and so it will be made available to folks if they were unable to attend today, because it's very interesting talks. Also, we're at a point where we had identified taking a break. How are people feeling about maybe taking a 5-minute break and then we could reconvene? Because how are we doing on our schedule? I think we're a little bit over, right?
We're perfect. We could
We're
take
perfect.
10 minutes.
Okay, well, let's take 10. So we'll be reconvening here at 2:30?
2:30.
Okay. Very good. Thank you. Also, folks that are listening online, if they could email us to identify so we can keep tabs of who's been participating, that would be helpful for our outreach efforts in the future. Thank you very much.
Yes. Sometimes we're like, we're at the beginning of the
whatever. I don't think anybody actually saw the statement.
Yeah.
Alrighty, folks, let's go ahead and get started again. So who is our next speaker? Pete McMahon. And just once again, I'd like to reiterate that if you're listening in online, if you could please send us an email, just reply to the appointment. It would help us keep track of our public participation associated with our public outreach. So thank you very much for doing that. And without further ado, here's Pete.
Thanks, John. Thank you guys for sticking around after the break. So I'm going to talk about regional patterns in the geochemistry of oil field waters in some of these fields that we've been talking about today. And by oil field waters, I mean things like produced water, injectates, water that might be disposed of in ponds, water that might be injected for enhanced oil recovery. So that broad category of water I call oil field water. Okay, good. So the purpose of the oil field fluids component of the regional monitoring plan is to build a library of oil field water chemistry, and then to use that library of chemistry to support field-specific investigations of fluid transport between oil and gas operations and protected groundwater. I've broken up my talk into 4 parts. I'm going to very briefly talk about the study areas and approach, and then talk in some depth about the results, and then have a summary. We sampled in 4 oil fields. Oh, lights are flashing. No worries. The darker the better as far as I'm concerned. We sampled in 4 oil fields in the southern San Joaquin Valley. In the Fruitvale field, which is on the east side of the valley, we sampled 6 oil wells, and we collected 2 injectate samples. In the Lost Hills field, which is on the west side of the valley, we sampled 9 oil wells and collected 1 injectate sample. And then in the Belridge fields, we sampled 7 oil wells, and we collected samples from 2 water disposal ponds that are adjacent to the south end of the South Belridge field. We collected samples from oil wells that were producing from a number of different formations, and they're shown here. So in the Fruitvale field, we collected samples from the Echegoan, Chinook, and Santa Margarita formations. In Lost Hills, we sampled from the Echegoan and Monterey formations. And then in the Belridge fields, we sampled from the Tulare, Monterey, and Tembler formations. These fields, as you already really know, have a long history of water and steam injection for enhanced oil recovery and water disposal. And I'm showing a bit of that history in this slide, where I'm showing the cumulative volume of fluid injection in cubic meters from 1960 to 2017. If you look at the red line, which is for Fruitvale, you can see early on it had the largest amount of fluid injection. But that was rapidly overtaken, and by 2017, South Belridge by far had the largest volume of injected, which is shown by the gold line, followed by Lost Hills, which is shown by the blue line. Well, because those west side fields have had a lot of injection, we wanted to take a closer look at the injection water budget in those west side fields, because injecting fluids into these formations can affect the water chemistry, which is what we're really interested in. And so here I'm showing total injection volumes for the 3 west side fields, and that's broken up into the percentage of injection used for enhanced oil recovery, which is shown in gray, water disposal, which is in black, and then well stimulation treatment, which would include hydraulic fracturing. That's in red. And you can see that by far the most water injection was for enhanced oil recovery. And let me, if I didn't say it, this is for the period 2014 to 2017. For enhanced oil recovery, about 70 to 100% of the water that's injected is recycled produced, or was recycled produced water. But in the Lost Hills field, about 30% of the injected water was groundwater. Water disposal was the next largest type of injection, and presumably essentially all of that water would be produced water. And then by far the smallest amount of injection is for well stimulation treatment, less than 1% of the injection, and roughly half to 90% of the water used for well stimulation treatments was coming from the California aqueduct during this period. So the approach, in order to characterize the variability of these oil field waters, it's important to sample lots of different places. And so we sampled important hydrocarbon production zones in each oil field. We sampled major components of the oil field water cycle. So for example, produced water, injectates, water in disposal ponds, different source waters. And we sampled wells with a range of injection histories in areas nearby to our wells. And then we analyzed all of the samples for the full suite of regional monitoring plan constituents. Where there were publicly available historical data, we also included those in our analysis. So this slide just shows you the constituents that we analyzed for, and I've broken them up into 3 groups. At the top just shows the constituents used to characterize inorganic and radionuclide chemistry. The middle group shows constituents used to characterize hydrocarbon chemistry, and the bottom group shows constituents along with those in the top and middle blocks that are used to understand fluid mixing, chemical sources, and geochemical reactions. Okay, so we'll turn to results now. And what I want to do is I want to focus on chemical differences between oil fields, between oil production depths, between injection water sources, and between injectate and pond water. And then I'm also going to have just a very brief note on our radium data. And just to remind you why we're doing this, we're measuring the chemistry to determine if oil field fluids mix with protected groundwater. So we know from our data that relative to protected groundwater, oil field waters typically have higher concentrations of things like chloride, sodium, boron, ammonium, radium, and hydrocarbon gases. The oil field waters typically have isotopic enrichment in things like water, methane, dissolved inorganic carbon. And so if these two end members mix, we'd expect the mixtures to have concentrations and levels of isotopic enrichment that would be somewhere between those two end members. And what would be really nice to know with respect to the oil field fluids is whether the chemistry is the same or different between things like oil fields, between production depths, different injection water sources, injection water versus pond water. If there are chemical differences between those kind of 4 categories, then we might be able to use those differences to differentiate which oil field waters are mixing with groundwater should we come across an instance where that's happening. And then also, if there's high level of vulnerability, that means that really we need to do oil field water characterization in each oil field. We couldn't just collect data from one oil field and expect it to be representative of the data from another oil field if the level of variability is high. And so, of these 4 things, oil fields, production depths, and so on, I'm going to go through each one in turn. And so we'll start with chemical differences by oil field. And here I'm showing the hydrogen and oxygen isotopes of water for data from Fruitvale in red, Lost Hills in blue, and Belridge in orange. And then that diagonal line labeled the meteoric water line, that just basically represents the average composition of precipitation globally. And so samples that plot close to that line contain a larger amount of fresh water. Samples that plot farther away from that line might contain a larger component of some other water source like seawater. Or maybe the isotopes have been altered in some way since the water entered the subsurface. But what the data are showing is that the oil-bearing zones in the Fruitvale field have been extensively flushed by meteoric water compared to the west side fields. And our data also tell us that that meteoric water has come off the Sierra Nevada mountains. For example, the Kern River, which drains the mountains and flows through the Fruitvale field. And although the water is meteoric, the data indicate that it was probably recharged in about the mid-Pleistocene or earlier, so it's old water. Well, meteoric water flushing has a major influence on oil field water chemistry. Once again, compared to the Lost Hills and Belridge fields, Fruitvale has lower concentrations of major ions, trace elements, ammonium and radium. It has more biodegradation of dissolved organic carbon and hydrocarbon gases. And so these plots at the bottom of the graph are just showing you concentrations of TDS, ammonium, and radium in the different fields. And they're just examples that show that the concentrations are lower in Fruitvale than the west side fields, in some cases substantially lower. And so the data clearly show that, yeah, there are chemical differences between the oil fields. There is one thing that seems to be similar between the oil fields. And here I'm showing hydrogen and carbon isotopes of methane for each field. And we actually don't see substantial differences in the methane isotopes between the fields. The data from all the fields plot in the thermogenic gas field, which it's thermogenic gas being gas that was generated at relatively great depths and high temperatures. And so thermogenic gas is a clear indicator of oil field fluids. Chemical differences by production depth. Here I'm showing oxygen isotopes of water, chloride concentrations in the middle, and carbon isotopes of dissolved inorganic carbon, all relative to the depth to the top of the open interval in the oil well that we sampled. And you can see for the oxygen isotopes and for chloride, the values increase with depth, both within fields and between fields. And we also note that things like radium and acetate concentrations also increase with depth. In contrast, if you look at the carbon isotopes of dissolved inorganic carbon, you see that the values actually decrease with depth. And so these data are just examples to drive home the point that the chemistry of oil field water varies with depth, both within and between fields. Now let's talk about chemical differences in injection source waters. And I'm going to talk about 3 examples. This first one has to do with groundwater used for enhanced oil recovery. Once again, I'm showing the hydrogen and oxygen isotopes in water. There's that meteoric water line that I talked about. But now I'm just showing data from diatomite wells that we sampled in Lost Hills, and those are shown by the blue symbols. And I'm showing data for groundwater from the Tulare Formation that's used for enhanced oil recovery. That's shown by the green symbols. And then those red numbers, they just show the average injection volume within 500 meters of the wells, where the injection volumes are in millions of cubic meters. You can see that sample at the top there at 0.05. It has very little injection nearby, and so we kind of consider that to be an unaltered formation water. But you can see that as the amount of injection near these wells increases, the isotope values shift away from that unaltered formation water and closer to the Tulare groundwater signal. And they plot pretty nicely along a mixing line between those 2 end members. And so you can use linear relations like this one to estimate the percentage of end members in mixtures like this. And I'll just remind you that from 2014 to 2017, about 29% of the water used for EOR in the Lost Hills was groundwater. One consequence of injecting relatively fresh groundwater into oil-bearing zones is that you could dilute the chemistry of the formation waters. And here I'm showing an example of chloride and lithium dilution. So I'm showing data from the exact same wells that I showed in the previous slide. You can see that unaltered formation water has relatively high lithium and chloride concentrations. But once again, as the amount of injection near these wells increases, the concentrations shift away from high values in the unaltered formation water to lower values in the groundwater. Let's turn to our second example, and this has to do with aqueduct water used for hydraulic fracturing. Again, we're starting with the water isotope plot, and now I'm showing you data from 2 diatomite wells that we sampled in the North Belridge field. These wells are located about 400 meters from each other and completed at very similar depths, so we kind of consider them to be paired wells. And I'm also showing data from the California aqueduct by those blue stars. For those 2 diatomite wells, they were both hydraulically fractured, but the I'm not coordinated enough to use that. That one up there, we sampled 2 years after it was hydraulically fractured, and the one below it, we sampled 2 weeks after it was hydraulically fractured. And you can see that the water isotope data indicate the presence of aqueduct water in that recently hydrofraced well. You see that shift in isotope compositions toward the aqueduct water. It's important to remember, though, about the hydraulic fracturing is that the volume of fluids injected for hydraulic fracturing is really minuscule compared to the amount of water injected for enhanced oil recovery and water disposal. Strontium isotopes also look like they could be a useful indicator of hydraulic fracturing fluids. Here I'm showing strontium isotope ratios versus strontium concentrations in the plot on the left. And I'm showing all of our data. And this sample there, that's the one that we collected from the well that was hydraulically fractured 2 weeks before we sampled it. And you can see its ratio is higher than anything else in our data set. And there could be a couple of explanations for that. One is that if potassium chloride had been one of the additives in the frac fluid, potassium chloride is often derived from sylvite. Sylvite is a mineral that is known to be isotopically enriched with respect to strontium. Or if there had been some potassium feldspar components in the frac sand itself, potassium feldspar minerals are also noted to be enriched in strontium isotopes. Those sorts of things perhaps could account for that elevated strontium isotope ratio in that hydraulically fractured well. Nevertheless, another important point to consider about hydraulic fracturing is that the chemistry that it imparts could be relatively short-lived. And in this plot on the right, I'm showing total dissolved solids concentrations versus weeks after hydraulic fracturing. The sample we collected 2 weeks after fracking is shown here with a TDS of roughly 25,000. The producer actually sampled that same well 1 week after fracturing, and that TDS is shown there at about 11,000. And then that paired well that we sampled 2 years after it was fracked, that one's over here at about 30,000. So you can see that there seems to be a relatively rapid re-equilibration of the TDS following hydraulic fracturing, at least in this particular example. Obviously, it's one example from many that are out there. Okay, so we've looked at injection water from groundwater and from surface water sources, but what about identifying injection of recycled produced water for EOR or water disposal? Remember, this is the water that represents the largest volume of injection in these fields. The more widely used tracers like chloride and water isotopes may not work if the injected water and the receiving water are chemically and isotopically similar. We just couldn't see a difference. But noble gases may help with this. And so here I'm showing noble gas isotopes in natural gas. And the noble gases we're looking at here are neon and argon. And these are data that Pete Berry published recently and that he presented to this group several months ago. So the noble gas signature for gas in oil zones unaffected by injection, they plot down here. The noble gas signature for gas separated from two different injectate streams in Fruitvale plot up here, and the signature of air is up there. As you can see that the injectate gas has a large component of air in it, and that the injectate gas looks very different from the gas in pristine oil systems. And so these noble gas signatures look like they could be a useful trace for distinguishing water that's been injected. And I also note here that we have data that also show that there's a large air component in injected water as well, not just injected gas, but injected water as well. And these tracers may also help distinguish naturally migrated fluids from migration associated with oil and gas activities like injection. Oops. So now let's talk about noble gas isotopes used to distinguish between injectate water and pond water. Once again, I'm showing noble gas isotopes, but now I'm showing data for krypton, argon, and helium. And here is a sample of Lost Hills injectate water. Okay, so here's injectate water now, and you can see that its noble gas signature looks a lot like that of air. So again, a big air component in there. This blue diamond up here, that is air-saturated water. So if you just let air sit and expose to the atmosphere, that's what its signal would look like. And then for reference, I'm also showing data for an aqueduct sample that we collected. That's shown by that blue, light blue star behind the dark blue triangle. You can't see it too well, but as we'd expect, aqueduct water looks a lot like air-saturated water. Most importantly in this slide, though, is that samples from 2 different ponds have noble gas signatures that also look like air-saturated water and that look very different from injectate water. So again, here's a set of tracers that may be useful to just distinguishing between injectate and pond water. So here's my kind of lame attempt to try to synthesize a lot of the things I just talked about into a conceptual model for distinguishing injected water sources. So if we had inorganic tracers like sodium, chloride, bromide, and lithium, we had isotope data for things like water and dissolved inorganic carbon, and we had noble gases. And we wanted to distinguish between unaltered formation water, which is shown by number 1 there, injected groundwater, number 2, recycled produced water that was injected, number 3, and pond water, number 4. We might expect the formation water, produced water, pond water to all have high concentrations of inorganic salts and to have high levels of isotopic enrichment. But it's only the formation water that would have a noble gas signature like the pristine system. The injected produced water, number 3, would have a noble gas signature showing air contamination. And then the pond signal would be over here looking something like air-saturated water. And then in contrast to that group, there's the injected groundwater, which we'd expect to have low concentrations of salts, relatively low isotopic enrichment, but like injected produced water, it would have a noble gas signature showing air contamination. And then finally, a quick note on radium before I wrap up. So we measured radium 224, 226, and 228 in our samples. And it turns out that radium 224 is the primary component in the oil field waters. And that's shown in this graph to the right, where I'm showing fraction of total dissolved radium versus the radium isotopes. And you can see that radium 224 accounts for the largest fraction of total radium. Well, it turns out radium 224 isn't usually measured in oil field waters, including in a large regional study of California oil fields that was conducted by Dogger back in 1996. But our data seem to indicate radium 224 is an important component of the radium inventory, and so that's something that might be worth measuring if future surveys are conducted. And then finally, just to summarize, we see large variability in the chemistry of oil field waters between oil fields, with depth in production zones in relation to injection processes. The variability is due to both natural and anthropogenic processes. The variability indicates that sampling in each field is warranted, so we can't take the data from one field and necessarily expect those data to be representative of another field. And a single set of tracers is insufficient to characterize the variability. I hope my conceptual model kind of helped drive home this last point, and that is that using a diverse set of tracers improves our understanding of the variability, and it also helps us understand mixing between groundwater and oil field water. That's it, thanks.
No questions? Ah,
Oh, there's one.
Mr.
Thanks. Will Stringfellow, Lawrence Berkeley Lab. This may be a little esoteric, but in water reuse from produced water, in terms of public acceptance, what we looked at some data we had that was also looking at isotopes, and my interpretation of it looked like a lot of the water that was actually coming out and being reused was injected water that had been returned. So is there, do you think, a role for these types of analysis in terms of trying to, is it less problematic water if it's water that's been put in and then withdrawn compared to water that's in the formation? Or is the chemistry still something that's of concern for in the context of water reuse? Is there a really big difference? The water is from the outside, but it's interacted with the formation and then it's returned. Is the chemistry pretty much the same in terms of things like arsenic or chlorides and parameters? Do you have a feel for that?
Well, if you're talking about injected groundwater.
Yeah.
Yeah, I mean, well, let's just go back. Yeah, so I mean, here we're showing, so the chemistry of groundwater with respect to lithium and chloride is here. When you inject it into the oil field formation, depending on the proportions of the two end members, it's going to be, the concentrations are going to be higher than that end member, but how much higher kind of depends on, what the fraction of this and that.
Is it purely a mixing thing, or is it how long that water has been in contact with the formation? Do you have any idea for that?
For conservative tracers like this, it's a mixing. It's just a mixing thing. But for other things that are more reactive, it could be more of a how long has it been in there and what has it interacted with? Yeah.
Interesting.
So it depends on the constituents you're concerned about, I think.
Any questions from the email? No? Thank you, Pete.
So I will be presenting some of the results of the groundwater sampling that we conducted at Lost Hills and Belridge oil fields. I'll start off with a brief overview of the groundwater monitoring that's already going on at the Lost Hills and Belridge fields for SB4 monitoring and other projects ongoing, and describe how the sampling that we did fits into that monitoring. Then I'll briefly go into a summary of our findings, just to keep in mind when I go through more detailed results of the water chemistry analysis. And then finally finish and put all of that results together from the geochemical analysis together in a conclusion. So at Lost Hills and Belridge oil fields, these are very active fields. There's a lot of projects going on. including aquifer exemption proposals in Lost Hills and North Bell Ridge, primarily the Tulare aquifer, injection projects, including waste disposal and enhanced oil recovery, surface disposal ponds, which includes waste discharge requirements for active sites and post-closure monitoring for historic sites, well simulation projects and areas excluded from monitoring. And currently there are 19 groundwater sites within the oil field boundaries that are being used to monitor for well simulation treatment outside those excluded areas. As part of the regional monitoring program, we collected a total of 35 groundwater samples. This was during 2014 to 2017. Primarily, we were sampling during 2016 to 2017, and we collected 2 additional samples during the exploratory work in 2014. We sampled monitoring wells, irrigation wells, water source wells, which Pete showed some of the results for, and lastly, industrial wells, and these are shown as the green triangles on the map. 12 of the sites that we sampled are inside the field boundaries and include those sites that are monitored for well simulation treatment. We sampled an additional 17 sites outside the fields. And this was to characterize groundwater up gradient, down gradient, and actually we included 3 inside the field boundaries that were not part of the well simulation treatment monitoring. We also collected 1 aqueduct sample as an end member characterization for well simulation treatment. Aqueduct water is used as a base fluid for well simulation. We sampled 2 sites at multiple depths, 1 near the Lost Hills field and 1 in the South Belridge field, down gradient of an active surface disposal site. Additionally, we collected samples from 16 oil wells, 1 injectate tank, 2 surface disposal ponds. And this was during 2014 and 2017. They're shown by the gray, blue, and orange symbols. And again, these were the results described by Pete. So for the methods, the USGS compiled and reviewed information on the Lost Hills and Belridge study area, including all available groundwater and produced water quality data, well construction information and geophysical records, oil field development history and injection data, and hydrogeologic features. And groundwater chemistry and produced water chemistry were compared to investigate multiple lines of evidence for potential migration of oil field fluids to groundwater aquifers. So as part of the produced water analysis, we looked at if we could see injection into the formations, and now we're looking to see if we can see a mixing between those formation fluids that may or may not already be mixed, and see if we can see indicators of those fluids in groundwater. That's the main objective of the study, is to determine if there's evidence of fluid migration and water quality changes near the oil fields. And more information about the review of historical data will be described more in the manuscript, but generally were not included in this presentation for time constraints. So in the comparison of groundwater and produced water, there's several different end members that we sampled. End members are potential source waters that can influence groundwater chemistry if they find a way of mixing and entering the groundwater aquifer. At the Lost Hills and Belridge field, source waters are formation fluids from oil and gas production zones. So these are typically brines that are extracted along with oil and gas production. Another end member is surface disposal ponds, and these typically include a mix of different formation waters. Sampled an injectate tank, which is treated and blended produced water, and these are waters that are injected for waste disposal or enhanced oil recovery. We sampled 3 water source wells that were completed in the Upper Tulare at Lost Hills. And there are also water source wells at South Belridge completed in the Lower Tulare, but unfortunately those sites are primarily inactive since 2010, and we were not able to collect samples from those during 2016 and 2017. So, so these different end members can influence groundwater chemistry. Like I said, if they find a way to migrate into the groundwater aquifers, some of the different pathways are percolation of surface disposal and lateral movement of these fluids down gradient of the fields outside the field boundaries. There's leaky wells and well bores that allow vertical flow across confining layers. And then there's natural sources like faults and fractures. Another potential pathway is injection into formations that are hydraulically connected to protected groundwater. There's injection for waste disposal and enhanced recovery, injection of groundwater for enhanced oil recovery, and this is groundwater that was produced within the field boundaries, and injection of fluids for waste disposal or steam, and this is primarily aqueduct water. So you've already seen the slide showing the different chemical constituents that we sampled for the regional monitoring program. I've highlighted in red the constituents that are in addition to the monitoring that's already ongoing at these fields. They're more specialized to help us try to trace some of that mixing between produced water and groundwater. And those are primarily DOC, the age dating tracers like carbon-14 and tritium, as well as some other geochemical tracers, including stable isotopes of dissolved inorganic carbon and isotopes of boron and strontium, as well as noble gases and atmospheric gases. So some of the principal observations from the groundwater chemistry analysis in comparison to produced water are groundwater adjacent to fields is distinctively different from groundwater overlying the fields. There's greater variability in groundwater at the Belridge field compared to Lost Hills. Geochemical and age dating tracers can be used to distinguish between groundwater mixing with produced water disposed at the surface and oil field fluids from deeper formations. And lastly, produced water from surface disposal ponds may be reaching the confined deeper groundwater that makes up the primary aquifer system. And this is through wells crossing confining layers and further monitoring of the deeper zone adjacent to the Belridge fields may be necessary. So we can go ahead and move on to results. Okay, so these are box plots of total dissolved solids on the top graph and number of detected hydrocarbons on the bottom graph. And this is divided by sites that are adjacent or overlying the fields. And you can see that typically sites that were overlying the fields had higher TDS and greater number of hydrocarbons as well as hydrocarbon concentration. So this isn't necessarily unexpected given the proximity, both lateral and vertical, of groundwater and oil reservoirs where there's intense development like there is at Lost Hills and Belridge. But the many different processes that affect TDS and other traces are needed to help understand patterns. So we're not just looking at salinity and hydrocarbons, we're looking at additional tracers. Okay, so several analyses were used to determine groundwater age and modern recharge at the sites. The mean groundwater ages were estimated from radiocarbon age dating of dissolved inorganic carbon, and the presence of post-1950s water are identified using tritium and sulfur hexafluoride concentrations, SF6, in groundwater samples. So in this figure, we see mean groundwater age on the x-axis and depth to top of perforations on the y-axis, and there is generally increasing groundwater age with depth. And these sites are divided by their TDS concentrations. So in blue is less than 3,000, orange is 3 to 10,000, and brown is greater than 10,000. And generally the TDS also increased with well depth. There are a couple of sites that had TDS greater than 10,000, and these sites were some of the more shallow sites, and these could be indications of mixing from fluids at the surface. So in a previous regional monitoring program study at the Fruitvale oil field, this was during 2016 and 2017, groundwater samples and produced water samples were collected in a similar study to the one that for Lost Hills and Belridge. And it was found that the Kern River, which runs through the southern part of the field, was a large control on water quality for that field, along with rock-water interactions. And this is, the Fruitvale field is on the east side of the valley and is generally in a very different setting than what we're looking at on the west side of the valley. So there are regional differences that can control groundwater quality. And at Lost Hills and Belridge, we may be seeing higher salinity that can be related to natural, just hydrogeologic differences. And those include higher salinity water from the coast ranges, which is a primary recharge for that area. And there's little precipitation due to the rain shadow effect across the coast ranges. And then there's that anticlinal structure that Jan talked about, where you have oil at the crest of the anticline, and so you see higher salinity waters at shallower depths. So the different water sources, in red is the Fruitvale groundwater results. You can see that those are plotted pretty close to the Kern River stable isotopes, and that is a good indicator that the Kern River is a major source of water for that oil field. In contrast, we have Lost Hills and Belridge shown as orange and blue symbols. I use the similar symbols as Pete's presentation, so we have Belridge as orange, Lost Hills as blue, and the produced water samples are shown as no-fill symbols. So the Lost Hills and Belridge groundwater samples typically plot along the local meteoric water line. There are a few samples that have evidence of mixing with evaporated water, and those are the sites that plot along that dashed line. So as you mix with more evaporated water, the stable isotopes are going to get heavier and move to the right. So we were seeing that with a few samples down gradient of surface disposal ponds that we sampled. So here I'm showing chloride versus boron, and we're looking at a few sites that are down gradient of surface disposal ponds that we sampled in the South Belridge field. The numbers show the distance of the site from the surface disposal ponds. So it's 1.2 kilometers to 4.8 kilometers. And these sites generally show mixing along a line with the produced water samples that were collected from the upgradient ponds. Also shown is results from a waste disposal well that was nearby that injects similar water that is disposed at the surface. So we can see some similarities between these sites that are down gradient of the ponds and the pond water chemistry. So there's a very extensive monitoring well network that's sampled to monitor historic effects of surface disposal at Lost Hills and Belridge, and those monitoring wells are shown as the black dots on the map, and those represent either one monitoring well or a pair of monitoring wells sampling multiple depths. So there's a lot of monitoring already occurring to look at the effects of the surface disposal, and this is regulated by the Central Valley Regional Water Board. And we reviewed some of the historical data for these sites. A lot of the information is available on the State Water Board's GeoTracker website. and the results of the monitoring are generally consistent with the tracers and mechanisms that we report today. Okay, so similar to the chloride versus boron plot, we're seeing similar trends of mixing with the other ions, so chloride versus iodide in the bottom left, and chloride versus bromide in the bottom right. So this is just a couple more examples of increasing chloride, boron, iodide, and bromide at sites that are down gradient of the ponds, and a few sites circled in blue that are overlying the Lost Hills field. Nitrogen can be used as a tracer of oil field fluids. We generally saw higher concentrations of ammonium overlying the fields, and in previous studies, it's been found high concentrations of ammonium in oil-producing formations at Lost Hills and Belridge. So ammonium was detected at all of the produced water sites that were sampled for the study, up to 460 milligrams per liter, and we were seeing concentrations up to 27 milligrams per liter at Tulare sites overlying the field. And this was greater than the background concentration of 1.4, and this was determined by looking at groundwater adjacent to the fields. So the presence of ammonium in groundwater overlying the oil field is consistent with an oil field fluid source, but additional tracers, of course, is needed to determine that. So high ammonium in produced water can add nitrogen to groundwater, which can manifest itself as other species, so nitrate and nitrite, as well as excess nitrogen. And this is because the process is known as nitrification and denitrification. So in the presence of oxygen, ammonium will be oxidized to nitrite and nitrate, which will then be converted to excess nitrogen gas. And we saw a few detections of nitrate, mostly overlying the Belridge field, possibly from the oxidation of ammonium after mixing with some oil field fluids. Nitrate was more common at the Belridge sites than at Lost Hills, and this was primarily sites that were partially or fully completed in the alluvium. Some nitrate from oil field ammonium was denitrified to excess nitrogen gas. The highest was down gradient of the ponds. So the excess nitrogen concentrations are shown on the map as the numbers. So we're seeing values greater than 5 at the sites down gradient of the ponds, as well as excess nitrogen at other sites adjacent to the fields. So this could be an indicator of ammonium that's been completely, or ammonium that's been oxidized to nitrate, which has been denitrified to excess nitrogen. Or it could also just have a natural concentrations of nitrate at these sites from crops that are adjacent to the fields. So nitrate input from oil and gas is important locally for understanding the different geochemical processes at the fields, but it's not considered a large input on a regional scale, which is primarily from agricultural. The sources of methane, we looked at isotopes of methane, and that is shown in the graph on the top right. And these isotopes indicated that the methane in samples was primarily thermogenic or mixed thermogenic and biogenic. There was also one of the sites that plotted, or that was located down gradient of the surface disposal pond, plotted in a region that indicated acetate fermentation. So the produced water ponds had high acetate concentrations, and in the fermentation process, we could be seeing the isotopic composition of methane at the site because of those processes. So at the Lost Hills field, concentrations of heavier hydrocarbons, that's ethane and propane, relative to methane. We're seeing that in the bottom right graph. The concentrations of the heavier hydrocarbons are lower than expected for thermogenic samples and higher than expected for biogenic samples. And that's why they plot between the biogenic and thermogenic squares. So it's basically showing additional processes for these samples. And in Pete's presentation, he noted that methane was pretty similar between the Fruitvale and Lost Hills and Belridge fields for the produced water samples. And we're seeing a lot more variability in the groundwater samples. So dissolved organic carbon, this was highest in groundwater at sites down gradient of Belridge mixing with surface disposal. So we're seeing concentrations of greater than 5 milligrams per liter. And DOC was actually lower at some of the deep sites at the Lost Hills field. So the Belridge sites are shown as the orange triangles. DOC was greater than about 10. And at Lost Hills at Lost Hills, the deeper Tulare sites had DOC a bit lower, just higher than 1. But the isotopic composition of dissolved inorganic carbon was generally different. So we were seeing heavier isotopic composition of DIC up to 27 per mil, and this can happen from the microbial degradation of DOC. So that could be why we're seeing lower DOC concentrations at these Lost Hills sites compared to Belridge. So there are additional tracers that we are currently exploring in collaboration with research labs for distinguishing between the effects of injected fluids and fluids disposed at the surface. So here we're looking at the same noble gas graph that Pete was showing, but we're looking at groundwater samples now. And there are a few sites that plot near that air saturated water sample, including the produced water pond that we sampled and a few of the down gradient sites. So we're seeing a noble gas signature that could indicate some mixing with water that's been exposed to air and become fully saturated. Radium isotope analysis is also ongoing with research labs. Here we're looking at chloride versus total radium. We see higher concentrations with some samples as well as in the produced water samples. And when we look at the different radium isotopes, we can see differences between the produced water results and some of the groundwater samples. And this could be from geochemical reactions as water enters the unsaturated zone from these surface disposal ponds and moves through the unsaturated zone before mixing with groundwater. So this could create some really unique radium isotope chemistry. And so we're looking more into that. So now we can start bringing that all together and looking at the different characteristics for each of the groups of sites. And so I grouped them into native groundwater adjacent to fields, groundwater overlying the fields that are possibly affected by deeper formation fluids, and also sites that are affected by surface disposal ponds. So looking at native groundwater first, the relative characteristics are generally, we're seeing pre-modern water mixed with younger water. These samples generally have no methane and few or no soluble hydrocarbons like BTEX. The samples have low salinity and concentrations of inorganics, as well as nutrients and DOC. And there's little isotopic fractionation of water and dissolved inorganic carbon. A few of these sites that fit into that category are highlighted in the gray circles. Freshest groundwater was adjacent to the fields at sites 3 to 5 kilometers away from field boundaries. TDS was generally 1,200 to 2,300 at depths between 60 and 200 meters below land surface. And these samples had no hydrocarbons. The groundwater affected by the migration of deeper oil field fluids have mostly pre-modern water. There's mixed thermogenic and biogenic methane. We're seeing high benzene and other hydrocarbons, moderate salinity and inorganics. And this is moderate relative to what we were seeing with the surface disposal sites, so between 3 and 10,000 mostly. These sites had high ammonium, low to moderate dissolved organic carbon, and enrichment of dissolved inorganic carbon isotopes. And this was by the process of methanogenesis, and that's the degradation of DOC. And also for these sites, we had little isotopic fractionation of water. So those plotted along that meteoric water line generally. Okay, so these sites are highlighted in gray, mostly sites that were overlying the Lost Hills field. We saw moderate salinity and the presence of natural gas. The TDS was around 4,000 to 6,000 milligrams per liter, methane up to 60 milligrams per liter, with a biogenic source at the shallower sites, and total hydrocarbons was up to 31 micrograms per liter. We also saw a small fraction of produced water mixing with native water at the edge of the field, which are pointed out. So these were a couple water source wells and another monitoring well in the south end of the field. And lastly, groundwater affected by produced water disposed at the surface. We saw the presence of post-1950s water as seen by the tritium detections. There was methane that was present primarily by fermentation, so a biogenic process. There was a contribution of air-saturated water that we saw with the noble gas results, and radium disequilibrium that I was mentioning with the radium isotopes that we're still investigating, as well as high solutes, so high benzene and other hydrocarbons, high salinity in inorganics, a moderate nitrate, some high DOC, and isotopic fractionation of water by evaporation, as well as enrichment of stable isotopes of dissolved inorganic carbon. These sites are highlighted. They're located in the southern end of South Belridge. One was two was down gradient of the two surface ponds that we sampled, and another one was further north. And considering the distance from the ponds that we sampled is likely affected by a different plume. So in conclusion, sites overlying fields generally have more saline waters and dissolved hydrocarbons than sites adjacent to fields, and have geochemical indicators of mixing with produced waters from deeper formations. Sites down gradient from sampled disposal ponds, including groundwater sites completed in both the unconfined and deeper confined aquifers, show evidence of mixing with water disposed at the surface. So I forgot to mention that a couple of those sites that were down gradient from the sampled ponds are completed in both the alluvium and the Tulare. So we use multiple lines of evidence to develop interpretations of the presence and processes influencing water chemistry at Lost Hills and Belridge. And collaborative efforts are ongoing with laboratories to further investigate some of the geochemical tracers such as radium and noble gases, and better understand the mechanisms controlling mixing of oil field fluids and overlying groundwater. With that, I can open it up to questions.
I'm the bad penny that keeps turning up. Where's the ammonium coming from? Do you have any idea on that?
Well, it's found primarily in the Monterey Formation. So I don't know if Pete, maybe you might know a little bit more about the produced water chemistry.
So in the produced waters, we see the highest concentrations by far in samples from the Monterey Formation, which is known to be enriched in ammonium both in minerals, so like ammonium-bearing feldspars, and they're also from the mineralization of organic nitrogen in the formation. So.
One of the reasons I mentioned it, in the Gulf spill, we picked up ammonia signal that we originally thought was coming out of the oil, but apparently was a byproduct of biological degradation, and we're picking up the ammonia signal for that. So are they really high concentrations? I didn't notice the graphics in terms of, is it, really, do you think it's biological activity breaking things down, or do you have an insight on that?
For the ammonium coming from organics, I think so. But as I mentioned, there's also ammonium-rich feldspars, and I think that's not biological.
Can you tell the difference with isotopes on those?
People have done that. I think the Compton reference that Tracy showed gets into that, but we didn't do that type of analysis.
Okay, thanks.
You mentioned the nitrate data. Is there, do you think, a way to distinguish nitrate sources from produced water versus the ag source that you mentioned? You went through the characteristics of the water down gradient from the ponds having maybe high nitrate, but also high other salts. I'm just wondering if there's something that you found that may be kind of an easy way to distinguish between an ag source of nitrate versus a produced water source of nitrate that came out of this?
Well, for this particular study, we were going by location. So a lot of the nitrate detections that we found were directly overlying the oil fields where there isn't agricultural activities. So that was one thing. I believe there's a way to distinguish between the two sources, maybe using isotopes, which we did not sample for this study. So we were basically mostly going with the location of these detections.
Any other questions?
I have a question. So just for people's information, can you describe, when someone were to go out, if someone were to go out in the field and collect samples and test them for noble gases, is that something that most laboratories would be able to analyze for? And is there a specific method or technique that you need to collect these samples to test for the different noble gases?
Yeah, so noble gases are difficult to collect. They're very susceptible to air contamination. So we were not actually able to collect noble gases at several of the sites overlying the field because of the pump that is used at these sites may allow for atmospheric exchange. And so that would be difficult when interpreting the data to know the difference between air contamination and air that you would see with a injectate. So it is a very specialized type of analysis, and I know of a few labs that the USGS contracts with, but I don't think it's a very common analysis.
So are they commercial laboratories, or are they research laboratories that do that?
They're research.
Research oriented, okay.
Yeah.
Right, I think that part of the reason why I'm asking the question, because I kind of already knew the answer a little bit, but it's that for people that are listening in and are in the room, there may be some instances where we would be entertaining the idea of doing additional analysis and having discussions on doing noble gas testing, and so having a better, broader understanding of what goes into those types of analyses, collection of the samples, et cetera, I think is helpful. Also, we have a question online, and it's in very small font. So it's from Laura Feinstein at Pacific Institute. Question for Tracy. You're finding that produced water from surface ponds may be reaching confined, deeper groundwater that makes up the primary aquifer system seems particularly significant. Can you please recap the evidence that led to this finding? Can you describe what is known about the primary aquifer system in terms of spatial extent, water quality, connectivity to surface water, and human use? That's it in a nutshell.
Well, I'll start with the first part of the question, and I might need the second part repeated. So the sites that we're directly downgrading of this pond are completed in the unconfined alluvium and in the confined Tulare zone. So that was one of the major concerns, is that if we're seeing contamination at these sites, that it could be affecting both of the aquifers. And as I said, there's a lot of monitoring going on, downgrading of the South Belridge field related to surface disposal, and a lot of these sites don't have current Tulare groundwater results. And so that's why we're needing additional monitoring to see if this contamination is moving through well bores into confined aquifer. So that's one major pathway for contamination reaching the Tulare aquifer.
So the second part.
Going to mention quickly that we also did do depth-dependent sampling in a long-screened irrigation well that was screened both in the unconfined aquifer and the confined aquifer. So in that case, we have profiles of chemical data that show that the water coming out of the confined part has a chemistry, that's mixed with, produced water pond water from above. So that's a case where we have direct evidence of that kind of process. And then from the other wells sampled, we have samples that represent composite samples from those wells and are inferring from the well construction and the chemical results that similar well bore processes of fluids moving down well bores from the unconfined into the confined are occurring using the array of geochemical indicators that Tracy described.
Okay, so let me put my glasses back on. So I think this is the second part of it. Can you describe what is known about the primary aquifer system in terms of spatial extent, water quality, connectivity to surface water, and human use?
So the Tulare aquifer in the study area has historically been used for irrigation and industrial use. There aren't many drinking water wells in the area, at least not in the last probably 50 years or so. And the extent of it, I think we were seeing a lot of the characterization of the Tulare aquifer from Lindsay's geophysical results. And depending on the area, it's fresher downgrading of South Belridge and higher salinity downgrading of Lost Hills. So one of the samples that we collected downgrading at South Belridge, we're looking at TDS of about 1,500. Fresh water for this area. Okay.
Right. So it is being used. I mean.
Yeah, it's definitely being used.
But the connectivity to the surface, though, is I'm not quite. Okay, so the response from Laura is, I think I understand what she means by the primary aquifer. Now she means the Tulare aquifer.
Oh, right.
Yes.
Yeah, I'm talking about the confined aquifer that's not exposed to the, or that's not unconfined or perched, like in the
Below the Corcoran clay equivalent
Correct.
that was described earlier.
Can I add one other? I think you may have mentioned this, but another line of evidence that you identified as potential evidence of mixing of waters coming from above, from the unconfined aquifer, and getting into the confined aquifer at times, is some of the historical data in the monitoring data sets showed a great deal of variability over time in water chemistry, very sudden changes. So the chemistry was almost bimodal. You would see very high concentrations sometimes and very low concentrations sometimes. And that was suggesting that you were having mixing of different sources of waters in those wells. And that was really in those historical well data sets that you were looking at. So I think the hypothesis was those sites may also be indicators of sites where we've got these processes of mixing of water from above, from the shallow plumes moving down well bores in places, intermittently affecting the composite chemistry that comes out of those wells. So that's another line of evidence to suggest that those kinds of well bore processes, mixing processes, well bores as conduits, out in the groundwater area may be an important process in this area. Did I miss anything there, Tracy? That was another line of evidence we talked about.
That sounds right, yeah.
Vertical movement within the aquifer system? Well, yeah, so in the Lost Hills, I mean, as Kim mentioned earlier in the overview, one of the reasons we wanted to drill multiple well monitoring sites, install wells at different depths, is to learn about directions of groundwater flow vertically between the different aquifer layers. And we've just begun collecting data at these sites, the Lost Hills multiple well monitoring site. We have recorders in the different wells. But there's really quite large head differences between the different layers. The groundwater flow directions appear to be, would tend to move groundwater from the bottom of the aquifer up to the middle, and from the top of the aquifer to the middle. So this particular site suggests that you've got vertical head differences that could drive groundwater flow, that would cause, you'd have physical gradients to move groundwater flow at this particular location. And so that's the sort of things we hope to learn more about with these multiple well monitoring sites in the future. And there isn't much data out there on those processes. And so that's part of what we're trying to learn more about the physics of groundwater flow driving changes in groundwater quality.
Run.
Thanks. This is Shahla Farnhook with DWQ. I think we're getting a lot of really good questions like the last one and also earlier on, impact of these studies on our aquifer exemptions. So my assumption and understanding is this is an opportunity for USGS to share your findings, your information, but as you getting more data and when you come up with the reports, there would be more detailed analysis that may be better, put you in a better situation to answer some of these questions, which obviously it's clear what the audience is interested to know is ultimately what these findings going to mean in terms of our decision making and our evaluations or any additional work that we may or the oil companies may need to do. Is that right?
Thank you, Shala.
Okay, so Kim, you have a wrap-up slide?
Find it. Some operational considerations, which are basically summaries of what's gone on as we've implemented this regional monitoring program. I think we said this last time in January that access to oil and groundwater wells for sampling has been one of our rate limiting steps. And you saw how neatly we had everything organized in timeframes. And you run into a rate limiting step, and that gets problematic to stay on time. The other thing is that we have a new step in our process where we are going to synthesize the information, the historical development of the oil fields, where the major fluid flows have been, and we are going to ask operators to give us some feedback on it and provide any additional information that somehow we missed in our synthesis, information that they may have that they're willing to be made public. And we will use that information to consider in our site criteria, sampling site criteria, and we hope that this will not be a rate limiting step. A couple of things I want to say about the historical data from scanned sources, being water chemistry, well depth geophysical logs. We're putting a huge amount of effort into compiling these into numerical databases. And Catherine might want to know this, but currently we don't have any state databases or portals that we can give the state this information to post in, to publish in. We're publishing the information in our data releases on Sybase, but you know, things like well construction data, there currently is no process for getting that well construction data into any of Dogger's WellStar systems, or the water chemistry data does not flow easily into GeoTracker either. So just wanted to flag that. The next places we're headed are, I think I talked about this before, just so you know, we're planning another public stakeholder meeting to give you some preliminary results this winter. And in that stakeholder meeting, we expect to, Matt, correct me if I'm wrong, we're going to be talking about Elk Hills, North Coast Levee, Oxnard, Orcutt, and Montebello. Montebello about a year from now. We're also going to be completing samples in these fields and the data tracking quality assurance and doing historical data analysis. So what's this? This is where we're planning to be in 2018 to 20, Kern River, Placerita, San Ardo, San Maria Valley, and the Buena Vista Midway Sunset Fields. So with that, that's kind of a picture of where we're headed. Does anybody have any questions? Does anybody want to engage in any deeper conversations about any of the technical issues that you've heard today that you didn't really have time to get into? Well, I know Will does, but we'll talk to you over beer later. Everybody's all brain dead. Okay. All right. Thank you very much for coming. Thank you very much for calling in on the phone. We very much appreciate your attendance. And John wants to say something.
I do. Thank you. And I just wanted to say thanks again to everybody for participating. And if you do have questions and you're listening in or you watch the webcast later, by all means contact our oil and gas staff, including myself. If you have any questions, we can forward that information to the USGS and have subsequent conversations if there's something that you'd like to discuss. Also, there's a form that Karen has at the back of the room, and I think we're going to email folks this form too, if they could please fill it out and send it back to us. And this is related to our public outreach aspect, performance measures that our program has in place. So once again, thank you again, and we'll see you again in 6 months. Thank you.